Hey, welcome back to ECE 382. Today we're getting into Module 6, the general purpose input-output pins. Last time you built your robot, so today we're going to actually start working with some of the hardware that you put together. Specifically, we're going to look at the MSP432 and what kind of input-output capability it has, and then we're going to get into some specific programming. How do we access the input and output capabilities of the MSP432? So look, you've seen the MSP432, you've worked with it now for a few weeks, and there are a number of different pins that we're going to be using. These jumpers here, these J1, 2, 3, 4, and 5, those provide access to the MSP432 GPIO pins. And there are over 100 pins on the MSP432. And of those, 184 are used for input and output. Each pin is combined into, pins are combined into ports. We've kind of talked about this a little bit before, and they're combined into 10 ports. And we can see those ports here on the left, GPIO port 1 through 10. So there's So when we're working with a different port, say pins port 7, 0 through port 7, 7, that's the 8 pins right here, and those are the pins that are connected to your line sensors that we'll be using later. So when we talk about ports and pins, just know that a port is 8 pins combined, and that allows us to access that entire port together, or we can access each pin individually. If we want to, pin 7.1 specifically would give us pin 1 on that port right here. There's 3 different types of I/O. Pins, and those are digital, timers, and analog, or really analog they're connected to analog to digital converters. So the digital includes GPIO, which are general purpose input output ports, UART, which is our universal asynchronous receiver transmitter, which we will go through a bit. And then 2 different types of serial communication, SPI and I2C, which we do talk about later. We talk about all 3 of these later when we start looking at serial, and we'll look at the differences and what they are. But today we're going to focus on general purpose input-output. And specifically in the lab for Module 6, we're going to look at the line sensors, which are connected to digital general purpose input-out-input. Like I said, they're connected here on port 7. But there's also a couple other components we'll see throughout connected to a couple other pins. And so the way it works basically is transistors are used to convert voltages into digital logic. So we're not going to go into a lot of detail on how that is done. That's covered in some of the other digital logic classes. But what you need to know is that depending on what the voltage seen from a sensor, and so everything in the real world, think of in terms of voltages. So when a sensor is receiving an input, it's going to be a voltage, which a voltage is a range of values. And that transistors, depending on how they turn on and off, are going to determine if that voltage represents a 0 or 1. And the way we do that is based off of these different models here. So these different models determine they map the voltages to different logic. So for example, let's look at MSP432 here, and what we see is a low value, or a 0, is with a voltage range of 0.0 to 0.825 volts. And you can see that here. And then a high, a 1, is 2.475 to 3.3 volts. Then we have this range in the middle, which is allows us to kind of differentiate between that low and high. And that range, if it's a voltage between there, it's undefined, and we don't try to pick one or the other. Just allows us to ensure that we know exactly what a high and a low is. So this is what's key for the MSP432. CMOS, 5 volt CMOS and 2.5 volt CMOS are two of the other common ones, and then TTL. And so it's important to know when you're interfacing with digital logic and different embedded systems, what kind of voltages correlate to different logic, and to make sure that if the system's expecting 5 volt TTL, that, or the sensor is expecting that the sensor can, or that the MSP or the processor can take that. So the MSP432 has different ranges, and so all the sensors have to be compatible with those ranges as well. There are two different ways to interact with input-output devices, and that is active high and active low. So with active high, what we're saying, and this is positive logic, is that a low voltage equals false, and a high voltage equals true. So when the switch is not, for example, the bump sensors on the robot, when the bump is not pressed, we're going to have a low voltage across. Obviously, it's not completing the circuit, low voltage, so that's going to be a false. And then when the button is pressed, there's going to be a high voltage, and it's going to be true. We can flip our logic and have negative logic, and in that sense, a low voltage will equal true, and a high voltage will equal false. And this might be beneficial because obviously it takes less power to have low voltage, and then therefore it's maintain that true. It also depends on what the switch is doing. So for our bump sensors, obviously pressing the switch is showing us that it's false until the bump sensor is pressed. Then it becomes true that we have hit a wall. But if we were trying to do something a little bit different, where maybe we want the sensors to stay pressed until they're released, and in that sense we might keep the sensors combined might be false, and then once the switch is released, then it becomes true, and that is that negative logic. And so the reason we use the pull down, or the positive logic, and it helps us with our just overall logic. We can do something along the lines of, if read the bump sensors, bump equals P4 in, and then we can do something along the lines of, if bump, and then if any of those, so if they're all 0, right, so no bump sensors have been hit, then as soon as one of the bump sensors is hit, it doesn't matter which one, the if statement, as long as any of these or multiple of them are 1, then this whole statement will become true. So if any of these is a 1, then that becomes true. Now let's think of this on the opposite way. What if we wanted to do something while not bump? So while we haven't hit a bump, then we're good to go. We can continue. So while not bump, so now we have still negative logic, and so while this is not true, then we're going to continue. So then that's the other way we can do it as well, is while there's not a bump, we'll just keep continuing to do something. Then as soon as one of the bump sensors hit, now this becomes false and we will break. So that using positive logic allows us to really have those really nice easy conditionals, and they're easy to read as well. So the way we do active high and active low, or negative and positive logic, is with a pull down or pull up resistor. So when nothing is pressed, obviously the circuit is broken, so it's grounded, so the value along PA5 here is 0, and we can see as soon as this is closed, the resistance is higher down here, so the voltage is going to flow right into there and become a 1. Now this is a little bit different, it's opposite. So while this is open, voltage is going to flow in here, so that's our true. Even though our switch is open, we're going to continue through, and it's going to be a high voltage, switch is open, false. But then as soon as the switch is closed, where we have that, the button pressed, our true state is now a low voltage. And so that's that negative logic. So when the button is pressed, we want to see a low voltage, and then when the button is released, we see a high voltage. All right, so let's talk about how we actually go in and program these different things. So to read from an input-output pin, there's 4 different steps. First, we have to initialize the port. So to do that, we set pin to GPIO. And for example, we say we want to make port 1, pin 1, an input. So we look here, and the first thing we need to do is set it as a general purpose input output. So let's just go over here and say our goal is to make P11 an input. Okay, so we know that we have to select these 2 registers. So these are registers. And if we look, this table is straight out of our I believe it's this one here. It's P432 Launchpad. But I'll confirm that and provide you guys the correct link to where these tables live. But here they are for you now. So the first thing we have to do is set both of these registers to 0. So sorry, I said that wrong. We want to clear both registers. So the way we clear, and if we look down at our table here, we can clear bits by ANDing with a 0. And that's why I provided you this little reminder down here. So if we look at the first step, we have to set the pin to GPIO. So to do that, we're going to take pin 1, or port 1, the select 0 register, and then AND that with not 0x02. Alright, so what do we do right there? So we took 0x02, which is that guy right there. We took the opposite of it, and then we ANDed that with whatever's in select 0. So for example, say select 0 right now for port 1, so that's that whole port. So this is, port 17, 1.6, 5, 4, 3, 2, 1, and 0. So that's the different pins. So let's just put it like this. This is port 1, pins 7, 6, 5, 4, 3, 2, 1, and 0. And each one of those pins has a select 0 register attached to it. And we just ANDed that select 0 register with the value 0x02, and then we took the NOT of it. So this is not 0x02, this is 0x02, and now we're going to AND that with the select 0. And so we don't know what's in here. This is all unknown to us, but what we do know is that if we AND it with the NOT of 0x02, I know that whatever is here is going to stay an x. This is going to be a 0 because ANDing with 0, no matter what this is going to be a 0. This is going to stay an x, 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 and x. Because whatever ANDing with a 1 just keeps it the same. And so what we've done now is, without changing any of the other pins, we have cleared the port 1, pin 1, select 0 value. And so we have to do that to make that a general purpose I/O pin, but we haven't changed the function of any of the other pins in port 1. Now if we wanted to do multiple of the port 1 pins at once, we could do that by changing, obviously, this binary value here. So we're going to do that twice, once for select 0 and once for select 1. So now we're going to do the same thing for select 1. We're going to AND that. And 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 equal, remember that just means we're going to AND it. We're ANDing select 1 with 0x02 and then setting select 1 equal. It's the same as like a plus equals, so that, int plus equals 2 is the same as int, sorry, let's just actually use a better variable name. So let's just say sum plus equals 2. That's the same as sum equals sum plus 2. That's the same thing we're doing here. We're just going to set port 1, so that's the same as port 1 select 1 equals port 1 select 1 and not 0x02. Okay, same thing. And now that clears the select 1 flag. So now both flags are 0, and we are set as a general purpose input output. All right. The next step is set the direction. So I'm going to erase this so it's out of my way. Alright, so we said we want to initialize port 1, pin 1 as an input. So we look here, and to do that we need to first set our direction pin to 0, or clear it, right? So again, same format, port 1, taking that direction register, and we're going to clear it by ANDing it with a 0, which is the same as ANDing it with 0x02. Again, that allows us to just have that second bit be a 0. So second bit referring to port 1, pin 1, be a 0. Everything else is a 1. Then that allows us to change just that 1 register without changing anything else. Alright, so we've set the functionality, we set the direction. Now we need to actually read from the port. We do that in 2 steps. First step, read from the port. And we can do that with pin 1 in. But the downside to that, so let's just say we want data to equal P1 in. Downside to that is we just taken everything from port 1, and so the next step is really select the bits of interest. Alright, and that's again right here, that's ending with 1. And so we can do steps 3 and 4 in one nice clean command, but let's just look at it in 2 real quick. So first we're going to take data, it's going to be equal to port 1 in, and then we're going to just take data and set it equal to, oops, that's a horrible and sign, 0x02. Alright, so now we're selecting that 1 bit of data, and now data only contains, because if data was here, right, and it's XX, when we AND it with 0x0, let's just put an X here because we don't really know what's in there. What we're going to get is 0x and a bunch of zeros. Alright, so that's ANDing those, and allows us to get that 1 bit of data that we cared about, but we can do both of these in one step with a nice clean line of code, which is just and then that gets us port 1, the whole input, and it with 2, so we're just getting that pin 1 data and storing that into data. Cool, so those are the 4 steps. Key to note. And what we're doing here when we're just changing the pin that we care about, because it'd be very easy to just select 2 and bring in everything or clear everything else, just set everything to 0, set all port 1 to 0, but that would really change the functionality of other systems. And when we only change the functionality or read in data that we care about, that is called friendly programming. And that's basically just changing functionality of bits you need without changing others. So that's key component to what we're doing here, because we don't know what those other pins are connected to. We don't know if they're driving the motors, the tachometers, or some other logic. So what we're going to do is we're just going to select the bits we care about and change those. Alright, so let's talk about now the output. Output's a little bit different for the kind of the same reasons, that friendly programming concept. So let's talk about how this works. So same first step, set to GPIO functionality. So let's say now we want to take port 1 pin 0 as an output. And what we're going to do we're going to take the not 0x01. So again, we have 0x01, that is 1, 2, 3, 4, 1, 2, 3, 1. Then the not of 0x01. And then we AND that with whatever's in select 0. we get everything stays the same except for that last bit, which turns into a 0. Same thing with select 1. And now we have 2 zeros. Now to GPIO. Alright, then we have to set the direction. And we want output this time, so we want to set it. So we're going to take and before what we did is we cleared. This time we are setting, and to set, we set with a 1. And that's going to be ORing with 0x. And we look down here, we typically will OR with the positive version, and that allows us to get that 1 bit set. So to look at that, we have direction, and we're going to OR that with 0x01. We're going to OR it. And when we're ORing, remember that or something with 0, it stays the same. So if it was a 0, it's going to be a 0. If it was a 1, it's going to be a 1. But if we OR it with a 1, we know for sure it's going to be a 1. So now we've changed just that one direction pin, set it to 1, we know it's an output. Alright, now the 4 steps to actually write to it. So the issue here is, say we have port 1, right? And let's say that we have in port 1 is this value right now. Okay? And we want to write to port 1, and we want to turn this off. We want to make it a 0. So we want port 1 to be 0. So if I wrote just zeros, what have I just done? I have just turned off every one of these pins in port 1. So say this pin here is connected to an LED, this pin here is connected to a line sensor, and then this here is connected to a LED 2. And so all my goal was turn off LED 2, but what have I done? I've turned off LED 1, I've turned off the line sensor, and I've changed everything else. So this gets back to that idea of friendly programming. So what I have to do to be able to friendly send an output to LED 2 and not without changing the rest, I have to first figure out what these, what these 7 bits are. So what is the output on those 7 bits? And I have to take those 7 bits, and then I have to change just the bit I want, and then I have to write all of that out to port 1. And so to do that, we can read from the port first. And this isn't the same as reading an input. This is reading the values that are on that output. So for example, we can take the old value equals P1 out. Okay, so now I've read from the port. We clear the bits of interest. And we have to clear them because depending on if we're trying to write a 1 or a 0, it's easier to do if the original bit is a 0. So we clear the bits of interest, which for us would be bit 0. We're going to set or clear depending on if we want it to be a 1 or a 0. And then we write to the port. And we do these 4 steps because that's a general case. Yes, if I was always clearing, then I wouldn't need step 5, but if I'm setting, I need to do step 4. So we do all 4. That way, if I'm trying to write a 1 or a 0, it works either way. And so that's why we have to do all 4 steps. So clear bits of interest, again, remember that's going to be old. And old and equals 0x01 for that one bit we're going to do. We're going to take our new and we're going to set it, we're going to OR, so say that's a 1 or a 0, we're going to OR that with the old, and then we're going to write to the port, which is equals new. Alright, so those are the 4 steps. So first we're going to get the old information, we're going to clear the rightmost bit, we're going to set it with the new, and we're going to OR it with the new, and then we're going to set it out. So let's just do 2 quick examples just so that we can see this. So first example, let's say we want to set it to a 0 and it was a 1, and then let's do that. So we take the old, so old's going to equal we're going to clear this. So now old, so this is 3, step 4, old equals, okay, then we are going to OR it with our new, which we're trying to write 0x01. So if we take xxxx and OR it with 0x01, we get xx1, and then 6, we send that out. Okay, so now let's look at the next example, and we want to set that to a 1. So that's our old. So that's step 3. 4, we're going to clear it, which doesn't change anything. Hold on, what did I just do? I ORed it with a 1. Okay, so that's ORing it with a 1. Let's OR when it was a 1. Now we're ORing or trying to make it a 1 when it was a 0. And then we're going to now OR it with 1 again. So our new becomes 1, and now we send that out. And so the reason that we do the clear is so that this works either way. And we can do that all in one nice piece of code, one line of code. So we can combine all those things. So that's the old here that we're going to amp and clear the bit of interest. And then we OR that with whatever our new value is. Okay, so hopefully it's pretty straightforward. It all comes back to the setting and clearing. The reason we're doing this 4-step process for reading is because we can't change the other values in that port, and we don't know what the previous value was, so we clear whatever the old value was, that bit of interest. That way we can write a new bit to allow us to do that. Because if we didn't do that, and this was a 1 before, and we wanted to change it to a 0, so let's just do that real quick. I know 3 examples. So let's say we didn't do the clear bits of interest, and our old information, again, we don't care, and that's a 1, and we're trying to, our new value is we're trying to clear it. So if we wanted to use the same step, but we skipped clear bits, we would go straight to ORing it, right? And so, oh, sorry, our new is 0, not 1. So we want to clear it, we want to set to 0. So now we go to OR it, so we OR x, 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 x with 1, and then we OR that with the zeros, and we get 1. Because ORing with 1 always gives us 1. So what this clearing bit of interest allows us to do now, so instead we would be clearing with a 0 here, and then we could then clear this down to a 0 just like so this was a 1 originally, we cleared it, we made it a 0, and now when we OR, it can stay a 0, and we're happy. And so these 4 steps allow us to just go clear to a 1 clear to a 0 or set to a 1 with the same 4 steps. So you can use this line of code here to write information as an output, and then this one line of code here to read information in. So those are the 2 key pieces of information I'm hoping you get out of this, if nothing else. And if you want to know why it works, I spent a good 10 minutes explaining it. Alright, so let's focus now on what that looks like with the lab today. So the lab is going to be working with the line sensors. And the way the line sensors work is you have an LED here that's going to emit a light. That light's going to reflect off a black or white surface at a different rate and charge a capacitor. That capacitor is then going to dissipate. So it's going to charge and then it's going to dissipate at a different rate depending on if it was white or black. And we can kind of see that, that's a great K, see that in this diagram here. So we charge the capacitor dissipates, and depending on when it gets to a certain voltage, so that voltage we will look at and see what that voltage is in the lab. Once that voltage goes, and here's a hint, it's probably based off this table, right? When we go from high to low. So once we take that voltage and it switches from that high range to that low range, the digital value is going to be 1, and then it's going to switch to a 0. And it's going to take longer to do that if it's a black surface. The capacitor is going to charge, differently, and it's going to dissipate slower. And so this is going to stay a 1 longer, and this is going to stay a 0 longer. So what we could do is, what we're going to do is we're going to charge that capacitor. We're going to wait a certain amount of time when I know that if it was a white line, this would be a 1 here, but it would be a 0 here. And if it was a dark line, it'd be a 1. So we're going to check and read the value right here. And if it's a 0, then we know it is a white line. And if we read the value here and it's a 1, we know it's a black line because of the rate of the dissipation of that capacitor and that voltage. So that voltage is going to take longer to get to the value that would represent a 0. And so if we see a 0, we know it's a white. And if we see it's a 1, then we know it's a black. So to do that, we're going to do these 7 steps. And this is what you're going to do in the pre-lab to get you ready for the lab. So the first step is you're going to take and set pin 5.3 high. So 5.3 represents the even. So what they've done, there's 8 LEDs. So let's go like this: 1, 2, 3, 4, or 8 line sensors, and the reds are connected to a 5.3 LED, and the greens are connected to 9.2. So what you're going to do is you're going to even LED, and then there's port 9.2 odd LED, and that's going to be the LED that charges the LEDs that charge the. Actually, it's one array of LEDs, so LEDs doesn't matter. It's going to charge that capacitor. That's this portion right here, and so there's the way this new line sensor works is one pin connects to 4 of the LEDs and the other pin connects to the other 4. So we're going to set both of these as outputs, and we're going to, in the actual, and this is the, I think it's called reflectance read. So we're going to set these high. So we're going to turn them on, basically. Alright, then we're going to set port 70 as an output and set high. So that's when we're charging this capacitor. Then we're going to wait 10 microseconds, and then we're going to set this as a, and there's a wait command. So it's clock underscore delay 1 microsecond, and then obviously some value here, hint 10 microseconds. This waits 1 microsecond per value, so maybe 10, I don't know. Then we're going to set port 70 through port 77 as an input, because what we've done is we've charged these capacitors. Now we're going to set it as an input. We're going to wait 1 millisecond, and really what we're going to wait, read takes in a time here, and it allows us to adjust that time depending on what our system is doing. And so we are going to wait time microseconds. So we're going to call this same function here, except instead of a value, say like this is going to be 10, this is going to be time. Then we're going to read and that's going to allow us to see what the value is. Is it a 0 or is it a 1? And that's going to tell us if it's a white or black line. So we're going to read all 8 pins, and then we're going to turn off LEDs. And then what that allows us to do, turning off the LEDs, allows us to save some power. So this is going to run at a certain rate. We don't need the LEDs on all the time because we're not always reading and charging or facilitating that capacitor. So we're going to save some power and turn off the LEDs. That is everything you need to know for the pre-lab and getting into the lab. Work through that pre-lab. You're going to write this reflectance.read function. So you're going to have to do these 7 steps. You're also going to initialize the different pins using these first 2 tables here, the table 10.2 and table 10.1. I owe you guys the reference for those, so I'll shoot that out in a Teams message. But everything else you need, you have. So get started on that pre-lab, and we'll see you in lab next time.